Hello, let's do some evolutionary game examples here. So I wrote these yesterday, and I've almost forgotten what they say, so hopefully I'll get them right. Okay, all right. So we got two phenotypes of population of dragons. Here's blue and reds. The dragons are colorblind, so I guess they don't choose who they mate with. And when they mate, here are the chances they will produce offspring of their colors. So if two blues mate together, they produce 100% chance. Um, and what are the equilibrium population distributions and which are stable. So in order to find the equilibrium population distributions, right, we have to check basically, right, there's all red, all blue, and then we have to look for a mix. Right, so a mixed version of this, right? And so in order to do that, we need to figure out, so if I'm red, right, so the blue, so let's do blue payoffs here. So, actually, I say P is going to be our percent blue, right? So then blue payoffs, or chances to reproduce, are going to be 1 times P plus 0.3 times 1 minus P, right? Because this is P, this is 1 minus P, so 1 and 0.3. And then for red, is equal to 0.7 P plus 1 times 1 minus P. Right? And we are looking for when those two are equal to each other. So 1P plus 0.3 minus 0.3P equals 0.7P plus 1 minus P. 0.3 plus 0.7P equals 1 minus 0.3P. P equals 0.7. Okay, and we could have guessed that just based on like the 0.7, 0.3 thing. It shouldn't be totally surprising that that's how it ended up. Oh. All right. So we got that. Now the question is which are stable. So our this is mixed at 70% blue. Okay, those are our three options. So the question is which of them are stable. So the way we do that, I'm going to erase these markings here, is I'm going to check the endpoints. The endpoints are always the easier ones to check. So all red. So if everybody's red, all right, but one blue. So all red but one blue. So basically, I can be blue or red here, but I'm only going to basically be playing against red players here. So if they're all red but one is blue, then blue payoff is 0.3, and red payoff is 1. So they're all blue, so they're all red and red is better, then this is stable. Again, if you're all red and when everything is red, red is better, then it's stable. Okay, that's going to mean that blue is also stable. Okay, so this means that all red are stable. This is going to mean that this one right here, not stable, and all blue is stable. So those two are my two answers. All right, so this is a game of three types of players. You've got swervers, people who go straight, and you got mixers who play 50-50. And 50-50, by the way, with this game, 50-50 is the mixed Nash equilibrium of this two-person game. So I made up these corners here. I calculated these. It's pretty simple. Like this is just the average of these two spots. So it's 0 and 1 and 0 negative 1. This is the average of these two, and then right, this is the average of this or this, whichever way you want to do it. So it's pretty easy to calculate that, and it's the average because it's 50-50. If it was not 50-50, then you'd have to like prorate it. So if it was like 75-25, if the mixture was 75-25, this would be like 0.25, negative 0.25. But regardless, is the mixed phenotype an ESS? So basically what this question is asking is, it can all mixed be invaded? Okay, so let's look at it simply here. So that means I'm saying like, okay, everyone else is a mix. We might have one of these ones. So let's just, what if I eliminate here and here? So, negative 0.5, negative 0.5, negative 0.5. Everyone is even in that case. So that's how we would do it. Obviously, in this case, it's all even, and that's because this is the mixed Nash. It actually has to work out that way. That's if the mixed Nash. If I chose some other numbers, it wouldn't necessarily work. But 50-50. So we're gonna do this. We have to do a little bit more advanced thought here. So what if I have no straight? Let's just do just swerve versus mix. Okay. Mixed is mix weakly dominates swerve, right? Mix does better than swerve. 0.5 is greater than 0, and negative 0.5 is greater than negative 0.5. So cannot invade mix, okay? Because mix is weakly dominant. Now I'm going to look at, what about straight? So let's get rid of swerve. It's a little bit trickier. But this, negative 1.5, is still slightly weakly dominant over straight. So straight cannot invade mix. Okay. So mix strategy, this is so all being mixed, all mixed is stable. All right. That doesn't mean mixed, but this is the alternative here is this doesn't mean mixed if like you just like threw a bunch of swerve, straight, and mixed together. It doesn't mean mix would end up eliminating the other two. It just means when it's already mostly mixed, mix will hold out. All right. So we got A's and B's. We know they're stable at 2/3 type A. And I want to know what, but we don't know what this particular outcome is. What happens when two A's interact with each other? So how do we deal with that? Well, we're still going to do it the same way. P equals percent A, which is 2/3, right? Which means that A's payoffs are equal to C times 2/3, right? C is 2/3, 1/3, plus 5 times 1/3. And B's payoffs are equal to 4 times 2/3, plus 1 times, or not 1, that's wrong, plus, right, because I'm doing 4 and 3 plus 3 times 1/3. And we set these equal to each other. So I get, this by the way simplifies, right? This is 2/3 C plus 5/3. And this is 8/3 plus 3 plus 1. So this is 11/3. So I got 2/3 times C plus 5/3 equals 11/3. 2/3 C equals 6/3. C we can cancel out, so it's alright. We can get this. This is 2C equals 6, or C equals 3. Okay, so that's this spot. So C equals 3, and this is in order for it to have a 2/3 type A equilibrium.